You're standing in a workshop somewhere on the Greek island of Rhodes, around 150 BC. There's no electricity. There's no glass lens ground precisely enough to focus starlight. There's definitely no computer. And yet the object sitting on the table in front of you has over 30 precisely cut bronze gears, interlocking with a level of mechanical sophistication that Europe would not see again for another 1,400 years. Someone in this room just built a machine that can predict eclipses. This isn't science fiction. This is Tuesday in the ancient world for the people who built the Antikythera mechanism. And here's the question that should be bothering you. If ancient people had this kind of engineering capability, why did it take humanity over 1,000 years to catch back up? Why does progress not just move forward the way we like to imagine it does? A smooth, upward line from cavemen to smartphones, but instead lurch, stall, vanish, and sometimes have to be reinvented from scratch. That's the real story here. Not ancient people were secretly geniuses, and not aliens did it, which no. The real story is stranger and more human than either of those. It's a story about how knowledge is fragile, how technology depends on more than just one clever person, and how entire civilizations can lose things that took centuries to build, sometimes within a single generation. Let's start with the mechanism itself, because it deserves the spotlight. The Antikythera mechanism was recovered in 1901 from shipwreck off the coast of a tiny Greek island, and for decades nobody actually understood what they were looking at. It looked like a corroded lump of bronze. It took X-ray imaging and later high-resolution CT scanning in the 2000s to reveal what was actually inside, a system of at least 30 interlocking gears, some with teeth cut to a precision of under half a millimeter, tracking the movement of the sun, the moon, and possibly all 5 planets known to the ancients. It modeled the moon's elliptical orbit using a clever gear-on-gear system that varied its own speed to match real lunar motion. It predicted eclipses years in advance. It even tracked the 4-year cycle of the ancient Olympic Games. Think about what that actually requires. Not just astronomical knowledge. The Babylonians and Greeks already had plenty of that on paper. It requires precision manufacturing. Someone had to cut dozens of tiny bronze gears with teeth accurate enough that the whole system wouldn't grind itself to a halt after a few rotations. That's not a hobbyist project. That's a workshop with specialized tools, specialized training, and probably years of failed prototypes nobody kept because they didn't work. And then, as far as the historical record is concerned, the whole tradition just stops. No later Antikythera mechanisms have ever been found. No detailed descriptions of how to build one survive. The technology that produced this object apparently existed in a very narrow window, in a very specific place, and then went quiet for over a millennium. Here's the pattern you're going to see over and over in this video. Extraordinary technical achievement, followed by extraordinary technical silence. Let's go to Rome, because Roman concrete is maybe the most infuriating example of this pattern for modern engineers. The Pantheon in Rome has the largest unreinforced concrete dome on Earth, and it was poured almost 1,900 years ago. It's still standing. Modern reinforced concrete structures, by comparison, are often expected to start showing serious structural problems within 50 to 100 years, especially anything exposed to seawater. Roman harbor structures, built out of a concrete mixture involving volcanic ash, lime, and seawater, have survived continuous ocean exposure for 2 millennia. Not just survived. In 2017, researchers studying Roman marine concrete found something modern materials science genuinely was not expecting. The concrete was getting stronger over time. Seawater percolating through the material was triggering the growth of a rare mineral called aluminous tobermorite within the concrete's microscopic cracks, actually reinforcing the structure instead of degrading it. Modern concrete does the opposite. Water intrusion is one of the primary things that destroys it. Modern engineers have spent years trying to reverse engineer this exact chemical reaction. And it's genuinely difficult because the process depends on a very specific type of volcanic ash from a very specific region of Italy, mixed using proportions the Romans never wrote down in a way that survived. We have some descriptions from the Roman engineer Vitruvius, but not a precise recipe. The people who actually built these structures were tradesmen, not scholars, and tradesmen in the ancient world passed knowledge down through apprenticeship, not documentation. When the Roman Empire fragmented and the trade networks and specialized labor pools collapsed with it, the specific craft knowledge of how to mix this concrete didn't get written into a book somewhere waiting to be rediscovered. It just stopped being taught person to person, and eventually there was no one left alive who had ever been taught it. That detail matters more than almost anything else in this video. So hold on to it because we're coming back to it. Now, let's go to Delhi, India, and look at a 24-foot iron pillar that has been standing in the open air, exposed to monsoon humidity, for approximately 1,600 years without rusting. If you know anything about iron, you know this should not be possible. Iron rusts. It's one of the most reliable chemical processes on the planet. Leave an iron nail outside for a few years and you'll get a flaky orange mess. The iron pillar of Delhi has been sitting outside since roughly 400 CE and has developed only a thin, stable, protective layer that has effectively stopped corrosion in its tracks for over a millennium and a half. Metallurgists studying the pillar in the 2000s found the answer, and it's genuinely elegant. The iron used contains an unusually high concentration of phosphorus and a very low concentration of sulfur and manganese, compared to iron produced in most other ancient forging traditions. That specific chemical composition, combined with a particular forging process, causes the formation of a thin crystalline layer called white on the surface of the metal, which acts as a passive, self-sustaining barrier against oxidation. Modern rust proofing often relies on active coatings, paint, galvanization, sacrificial anodes, things you have to reapply and maintain. The iron pillar figured out, over 1,600 years ago, how to make the rust resistance part of the metal itself permanently with no maintenance required, ever. And once again, nobody wrote down the exact recipe in a form that survived intact. Indian ironworking guilds of that era operated on inherited hands-on craft knowledge, refined over generations of blacksmiths who understood which ores to use, how hot to forge, how long to work the metal, through direct experience rather than written chemical theory. Because the underlying chemistry of phosphorus content and crystalline layer formation wasn't something anyone in the ancient world had the tools to actually measure or describe scientifically. They knew it worked. They didn't necessarily know why, in the terms we'd use today. And when that specific tradition of ironworking eventually declined, replaced by different sources and different techniques as regional trade networks and metallurgical practices shifted, the specific combination that produced this one pillar's remarkable resistance essentially became unrepeatable. Let's do one more before we get to the theory that ties all of this together, because this one is almost uncomfortably clever. In 132 CE, a Chinese polymath named Zhang Heng built the world's first seismoscope, a device that could detect the direction of a distant earthquake using nothing but a heavy pendulum, a set of dragon mouth levers, and gravity. The device was a large bronze urn, roughly 6 feet across, with 8 dragon heads positioned around its rim, each holding a small bronze ball in its mouth, and 8 bronze toads positioned beneath them with open mouths. Inside, a sensitive pendulum mechanism was tuned to respond to the specific, subtle ground vibrations produced by a distant seismic wave. Not local vibration from someone walking by, not a passing cart, but the particular signature of an actual earthquake, hundreds of miles away. According to the historical record, in 138 CE, the device released a ball from one of its dragon mouths, indicating an earthquake to the west, even though nobody in the capital had felt any shaking at all. Days later, a messenger arrived reporting a major earthquake had struck a region hundreds of miles to the west. The device wasn't just a curiosity. It was detecting real seismic events before word could physically travel there on horseback. Modern seismology didn't develop a device capable of reliably distinguishing distant earthquake vibrations from local noise until the 1800s. That's a gap of over 1,700 years. And here's the frustrating part. The original device itself doesn't survive. We know its internal mechanism worked, based on detailed textual descriptions written by later Chinese historians. But the actual engineering specifics of how the pendulum and lever system was precisely calibrated to filter out irrelevant vibration were never fully preserved in enough technical detail for anyone to build an identical replica with full confidence. Modern reconstructions exist, and some of them do work, using assumed mechanisms based on the old descriptions. But there's genuine scholarly debate about whether they precisely match Zhang Heng's original internal design, because the fine mechanical details simply didn't make it through 17 centuries of copying, translation, and political upheaval intact. So now you've got four wildly different technologies: an astronomical computer, a self-healing building material, a rust-immune metal alloy, and an earthquake detector, from four completely different civilizations, separated by centuries, and every single one of them shares the exact same fate. Extraordinary, then gone. Not destroyed, necessarily. Just lost, forgotten, unrepeatable for 1,000 years or more, until modern science circled back around and had to reverse engineer what these people had already figured out. Here's the theory that actually explains this pattern, and it has almost nothing to do with intelligence and everything to do with how fragile knowledge transmission really is. Technology isn't just an idea. An idea is cheap. Anyone can have the idea, what if metal didn't rust? Or what if I build a machine that tracks the moon? The hard part, the part that actually took centuries to develop, is the accumulated, hands-on, often undocumented craft knowledge required to physically make the idea real, reliably at scale. That kind of knowledge doesn't usually live in a book. For most of human history, it lived in the hands and memory of specific individuals, master craftsmen, guild members, workshop apprentices, who learned it directly from other specific individuals through years of physical practice, trial, error, and correction that never got fully written down because writing it down wasn't how the knowledge was actually transmitted or valued at the time. This is called tacit knowledge, and it is brutally, structurally fragile in a way explicit written knowledge is not. A book can survive a fire in one library because copies exist elsewhere. A piece of tacit craft knowledge, held only in the trained hands and memory of a small number of specialized artisans, can be permanently lost the moment that small group of people dies, gets displaced, or simply stops finding apprentices willing to spend a decade learning a dying trade. You don't need a catastrophe to lose this kind of knowledge. You just need one generation where nobody bothers to fully pass it on. And history is absolutely full of exactly those moments. The Roman Empire didn't get hit by a single dramatic event that erased concrete making. It fragmented slowly, its trade networks and urban labor markets contracted. The specific volcanic ash trade routes serving Roman concrete workshops fell apart, and the specialized tradesmen who knew the mixture eventually died without training enough replacements, because the massive infrastructure projects that had employed them for generations simply stopped happening. Ancient Chinese metallurgical and mechanical traditions went through repeated disruptions from dynastic collapse, war, and shifting imperial priorities, each disruption another chance for a narrow, specialized lineage of craft knowledge to quietly die out. Ancient Greek precision bronzeworking, the kind capable of producing something like the Antikythera mechanism, appears to have depended on an extremely small, specialized tradition, possibly centered around one particular workshop or teacher-student lineage. And small, specialized traditions are exactly the kind of knowledge most vulnerable to vanishing without a trace the moment something disrupts the chain. This is the same brutal math you'd see anywhere else specialized knowledge concentrates in too few hands. It doesn't matter how brilliant the original innovation was. If the number of people who deeply understand it is small, and the mechanism for passing it forward depends entirely on person-to-person apprenticeship rather than robust, widely distributed documentation, that knowledge is one bad generation away from extinction. Cities get sacked, trade routes get cut, wars kill skilled tradesmen along with everyone else. Plagues don't care how good your craftsmanship is. Political instability disrupts the economic demand that justified training new apprentices in the first place. And once the last person who actually knows how to do the thing is gone, the how disappears with them. Even if the finished object, the pillar, the dome, the bronze mechanism, physically survives for centuries afterward as mute evidence that somebody once knew exactly what they were doing. This reframes the whole ancient technologies were ahead of their time idea in a much more useful way. It's not that these civilizations were smarter than the ones that came after them. It's that human technological progress isn't actually one continuous accumulating line, the way we like to picture it in a school textbook, marching steadily upward from stone tools to smartphones. It's closer to a scattered archipelago of isolated peaks, each one built up slowly through specific concentrated knowledge in specific places, and each one vulnerable to sinking back underwater the moment the conditions that supported it, trade, stability, demand, a living chain of teachers and apprentices, go away. Modern civilization is not actually immune to this, and that should be the uncomfortable part of this video for you. We like to imagine that writing everything down and putting it on the internet has solved the tacit knowledge problem permanently, that nothing important could ever be lost again the way Roman concrete or Zhang Heng's exact mechanism was lost. But a huge amount of modern manufacturing and engineering knowledge is still deeply tacit, still concentrated in the specific experience of specific aging workforces, and still not fully captured in any document anywhere. There are entire categories of specialized manufacturing. Certain precision optics, certain alloy processes, certain vacuum tube and analog electronics techniques, where the people who actually know how to do it by hand are retiring. And companies are genuinely struggling to fully capture and transfer that expertise before it walks out the door for good. NASA has, at points, had to essentially reverse engineer its own 1960s and 1970s manufacturing processes because the specific tacit knowledge of exactly how certain components were hand-built during the Apollo era wasn't fully documented, and the specific technicians who knew the fine details had retired or passed away. That's not an ancient civilization losing a secret formula for concrete. That's the modern world, right now, quietly losing its own version of the exact same thing. So when you look at the Antikythera mechanism sitting in a museum case, or picture the iron pillar of Delhi standing untouched in open air for 16 centuries, the right reaction isn't just ancient people were mysteriously ahead of their time. The more accurate and honestly more unsettling reaction is knowledge is far more fragile than the finished object it produces. A civilization can build something brilliant and durable enough to physically outlast itself by 1,000 years, while simultaneously losing the fragile, human, hands-on understanding of exactly how they built it, sometimes within a single generation of neglect. The gears keep turning long after the people who understood them are gone. The dome keeps standing. The pillar keeps not rusting. And somewhere out there, right now, there is very likely a piece of specialized, undocumented, entirely human knowledge sitting in the hands of a small number of aging experts, one retirement or one bad decade away from becoming the next thing some future civilization has to dig up, stare at, and spend 100 years trying to figure out how anyone ever managed to build it in the first place. What do you think we're quietly losing right now that people 200 years from now will have to reverse engineer? Let me know in the comments.